and then refill that known mass of reactants. When we're given that known mass of reactants, so let's say M for reactants is known. And then we must work out how much the product. So when we're given the known mass of a reactant and are asked to find out how much product is formed, né? Then we calculate the theoretical yield. So M is known or given. Let's rather say given. So M is given. Then we calculate. Theoretical yield, né? Based on how much product is formed. When M for the reactants is given, then we calculate the theoretical yield. Because we are asked to calculate mass of product formed. Now, when this happens, it's on paper. Ne? So this is just on paper. Theory. So because it's not what's really happening in the reaction, we call it theoretical yield. So in the laboratory, chemists almost never get this amount of product. So in other words, when they get when they actually get to react with each other. And ideally change so it means the actual yield is different. So in reality, what we calculate, or rather what results, is not the same as what is calculated. So let's be RDS, so like let's say which example can I use? Okay, so sometimes like a pocharo to namela taxi skolo. Then what's about to namela ka 60? That's at least to pocha so to namela ka 60. But after stopping, for some reason, taxi maybe after 15 minutes, so it means to namela ka quarter past 6. So although that's not really a reaction, chemistry, but it's to illustrate the idea already. Sometimes things don't go as planned. So what actually happens is different from theoretical. Ne? So what actually happens is different from theory. Ne? And the importance of knowing this is because in each step of a reaction, a small amount of product or reaction or reactant is lost, either because a reactant did not completely react or some other unwanted product are formed. So you can never really predict what's going to happen in the reaction. You might think or fisher magala ka moka ga dia braai ga Christmas because expect le batho ba bantši, but then I'll fitla aba twa fitla aba fitlile ba bantši, then I'll shumiši magala ka moka, then I'll shumiši dijo ka moka, etc. Or even if that's the case, maybe some other people might come and then they're even more than what you had planned, and then that results in an unwanted situation where some people are not gonna eat. So there's the planning part, the theoretical part, and then there's the actual part, the doing part, which is the actual part. So what happens, or rather what is calculated, is not always the same as what actually happens. So what does this tell us? This tells us that we have a part that is theoretical, and we also have a part that is actual. Okay, so when we have a part that is theoretical and a part that is actual, then the amount of product that we actually get is called the actual yield. Then we can calculate the percentage yield with the following equation. So percentage yield is actual yield divided by theoretical yield, and then multiply 100. So this is a standard way you calculate the percentage. So far, all right, so then we're gonna do one calculation, and in this calculation, refuah sulfuric acid H2SO4, and it reacts with ammonia NH3, and it produces a fertilizer. To produce fertilizer. And this fertilizer is NH4 Jepedi combined with a sulfate ion. Alright? So we must find the theoretical yield of ammonium sulfate. So we must find theoretical yield of, I'll just write here fertilizer, that can be obtained from 2 kilograms of H2SO4. So if you know it's agriculture school, that's great. You know what a fertilizer is, right? And so we must find fertilizer that can be formed if 2.2 kilograms of fertilizer is formed. Again, before we even continue, we must start first with balancing the equation. That's the first thing we start with. So we balance equation. And how do we balance it? Sulfuric acid arena, it's aqueous, and retlhakantsha ammonia, which is a gas, and then it will refer that ammonium sulfate. So we start there. This chemical equation is balanced because we've got 2 hydrogens plus 6 hydrogens. 2 times 3 is 6 plus 2 refer 8. On the left hand side, hydrogen is 80, and on the right hand side, hydrogen is 80 because the 2 multiply these 4 refer 8. So that checks out. And then the second element we look at is sulfur. Kamo left get a, kamo right get a 1 1. Then level oxygen. Kamo left get a 4. Kamo right get a 4. So it's 4 4. That checks out. Then level nitrogen. No. All right. Then nitrogen and then it's 2 times 1. It's also 2. So then we get 2 2. So everything checks out, yeah. Now because everything checks out, we can then proceed. Oh, let me not. I'll just do a new page. You can proceed with the next step. Now in the next step, I'll just write here, we check, ne? Check elements for balance. Then the next thing we do, we calculate the number of moles of the given substance. So what feel sulfuric acid again? H2SO4 is given, and then number of moles of H2SO4, its mass ever filling yona divided by the molar mass of the elements combined, and this equals sulfuric acid ever fill how much? 2 kilograms, ne? 2.0 kilograms, and then 2 kilograms is 2,000 grams, and we use grams because molar mass which use grams per mole, not kilograms per mole. So that's why we shift. So we convert units to grams because molar mass they have grams per mole, etc., not kilograms per mole. Now on the periodic table, when we add the molar masses of hydrogen, sulfur, and 4 times oxygen, what we will get is that the molar mass is 98.12 grams per mole. Then the number of moles are 2,000 divided by 98.12. It's just over 20.3. It's just over 20 moles, ne, of sulfuric acid. Okay. So far, yakwa. So the molar mass, yeah, A. Oh, okay. Yeah, it's just fine. Yeah, for. So yeah. So the feature is just over 20 grams per mole. Okay. Then also we must find the mole ratio. So because re dilaga sulfuric acid and we need to find the theoretical yield, yeah, in the percentage yield. Sorry, we need to find the theoretical yield. Yes, that's what I was correct about. Of ammonium sulfate. We look at the reactant filling information in our sulfuric acid, and they gave us all its details. So we can use then, because the product in a sulfate in it. So we'll have to use, because our product ammonium sulfate, our product ammonium sulfate, ne? This one. Wait, let me share this. So that one way I'm circling up, I haven't shared that, that's why. So this part here, yeah, the product in a layer sulfate. So look at this one. On top of that, butterfly information guy. In any case, ammoniac gas. So maybe they're not very fussy about how much gas of ammonia is gonna go. But I think they would, because I mean it probably costs some money. So they'll need to know how much it costs. Nevertheless, where were we? Oh, it was here. Then the next thing is to work out the mole ratio. So, kamo equation in rena 1 sulfuric acid plus 2 ammonia deriva 1 ammonium sulfate. So the ratio of reactant to product is 1 1. Let's see, mole ratio. So we can then write mole ratio. Then Ilva 1, and this is 1 1. And this is because sure, I'm feeling so weird right now. 1 1. And this is because oh, yeah. There is 1 mole of H2SO4 and 1 mole of NH4SO4. NH4 times 2 SO4. By the way, this one, committed to memory, it has a tendency to donate electron, but then so okay, plus 1 valence, we'll just call it valence for lack of a better word, and yeah, innerly plus 1 valence, and behaves like a group 1 element. Okay, therefore number of moles jar H2SO4 get 20,383 and number of moles jar ammonium sulfate le tsona ke 20,383 mole, ne? So we ride with that one. We go with that one. Okay. Then the next thing we're going to look at, is the following. So the maximum mass of ammonium sulfate, we can calculate it. Ammonium sulfate, we can find its molar mass on the periodic table. Oh yeah, this is what I just wrote. So, another 1 mole of H2SO4, kamo, and 1 mole of ammonium sulfate. Ne? Therefore, the number of moles ja H2SO4 is the same as the number of moles ja NH42SO4. That's why we have this conclusion there. So now that we have that conclusion, this conclusion here. So now that we have that conclusion, we go now to find the maximum mass of ammonium sulfate. And maximum mass is because we are calculating. When we calculate, that would be the like on a mass otafeta that kilo, that mass wa this that we calculate, because it's what is theoretical, and it's also based on the quantity in the 2 kilogram of amount of sulfuric acid and the 2.2 that is formed at the end of the reaction. So now in step 4, reach the formula number of moles, and I get read here for NH4 SO and NH42SO4, and then we're gonna lay mass of NH42SO4 over molar mass of NH42SO4. So we know this quantity, the molar mass, recalculate again, and this number of moles, recalculate, and we know the molar mass. So what we can do is make this one the subject of the formula, and then work out the mass. So we cross multiply, and then the mass becomes number of moles times molar mass, and this is 20,383 something times the molar mass of ammonium sulfate. Again, we also get from the periodic table by finding the molar mass of each element in the molecule and then adding them up. That one is idea, the molar mass of an atom, of an element, sorry. Okay, great. So I'm not going to repeat that one. So then we can say, okay. So then we'll have 114,04 grams per mole. And then our answer is 2,324,477 grams. And our answer is in grams because of that thing there. That grams there. And we can convert this to get kilograms by dividing by 1,000. So this becomes 2,34 or 324 kilograms. Now this is the theoretical. Why? Because it's calculated. But now, in our original statement, they tell us that 2.2 kilograms of fertilizer was formed. So if only 2.2 kilograms of fertilizer were formed, then it means actual yield, which is what happened in the reaction. So actual yield is 2.2 kilograms NH4 NH4 2SO4, but theoretically we found that it's 2,324 kilograms. So I wonder there's a difference there. A theoretical and it confirms the original theory to Mlinga. Things don't happen as we calculate. So we might calculate a theoretical yield and it will give us 100, but in actual 100 units of whatever it is that we are calculating, but in actual sense, we get 95 or 94 or 98, alright? But we'll get like a difference. So now we must find the percentage yield, and this equals actual yield over theoretical times 100, and that's 2.2 over 2.324 times 100, and that gives us, give a guy when you punch that into your calculator, should be 90 something. Or 4.64. You get it. You get it.
That's 94.67.
94.67, if you don't get it, forget about it. But you get it, eh? All right. So yeah. Okay. So now we understand the difference between theoretical and actual yield. All right. Then there is another type of problem where we calculate the mass of reactants and products. So here we find mass of reactants and products. It should be interesting. And in this example, we're given barium chloride. So BaCl2 plus sulfuric acid. And then it gives us barium sulfate plus some hydrogen chloride or hydrochloric acid, I suppose. Okay. And then they tell us that if we're given 2 grams of this BaCl2, what quantity in grams of sulfuric acid will we need in the reaction so that all of the salt, barium chloride, is used up. So we need to find the mass of sulfuric acid. Ne? If we're given 2 grams of barium chloride, then we must find mass of H2SO4 needed to react with all the BaCl2. Alright, and how do we do that? Let's see. We can find the number of moles of barium chloride, and we use the formula small m divided by big M. Small m is 2 grams for barium chloride. It's given, is this one. And then the molar mass we find from periodic table. And the answer is going to be 208.2 grams per mole. Then the number of moles was 0.0096 moles. It's a very small amount of moles, but it makes sense because 2 grams kenyani. 2 grams kenyani. If you think about it, roughly teaspoon is 5 grams, roughly. So 2 grams, it's like wesobile kila wana a tshela letswai mo dijong wa pe ebe ha o shumishi lepola mara o soba letswai ka menwana so then wa tshela mo dijong. 2 grams is about that amount. So it's not a lot of moles, it's like 0.096, not even 1 mole of that barium chloride. It's very far from 1 mole. Then in the second step, we find the number of moles of sulfuric acid. How do we do that? In our chemical equation, another 1 mole barium chloride and then another 1 mole sulfuric acid. Then this also means if we 1-to-1 kamkhoki, this also means the same number of moles of sulfuric acid must be used because mole ratio rena ke 1-1, where this is barium chloride and this is H2SO4. Then what do we do next? So we can therefore say number of moles of H2SO4 equal to number of moles of barium chloride and it over 0.0096 mole. So even now, we're not going to use a very large amount of sulfuric acid because if the number of moles is so small and it's much smaller than 1, the mass is also not going to be that big. The third thing we can do, because now we must find the mass of sulfuric acid that will react with all of the barium chloride. And we're gonna use the formula NH2SO4 elegantly the mass of H2SO4 over the molar mass of H2SO4. And the number of moles is 0.0096 mole. The mass it's M of H2SO4. But we do know the molar mass of sulfuric acid. And again, this we get from periodic table. Now, the molar mass is over 98.12 grams per mole. Then the answer that we get for the mass of H2SO4 required to react with all of the barium chloride is gonna equal 0.0996 times 98.12. Okay. Torfa 0.94 grams. So it's just under 1 gram of sulfuric acid that's gonna go into the reaction. Can you see it? What's this? All right. So I see 2-inch sulfuric acid inch. It's like maybe a drop or even less than a drop. Maybe a drop or even less than a drop. All right. Then the next thing that we're gonna do is find the moles of So this answers question 1. Or rather part A. Then part B, what must we do for part B? In part B, we must find the mass of hydrochloric acid or HCl that is produced during this reaction. Okay. So renal information ka barium chloride. We can use that information to find stuff about the HCl, the hydrochloric acid. Ne? And what do? We can find the moles of hydrochloric acid. So our reaction is BaCl2 plus H2SO4. Therefore, BaSO4 plus 2HCl. So, we've got our checker mole ratio, 2HCl and 2HCl. It's a mile whenever we have one of each of these reactions. So every time you add 2HCl every time. Now what does this tell us? If the number of moles are BaCl2 reserve, the number of moles are H2SO4 reserve, then we can say if number of moles of BaCl2 is 0.0096 mole, then number of moles of HCl is over 2 times 0.0096, and this becomes 0.0192 mole. Then once we have those moles, the last thing that we can then do is to find the mass of hydrochloric acid based on this formula, and since you have 0.0192 moles, the mass we don't know, but the molar mass, our check periodic table, it gives us 36.46 grams per mole. And the answer here is 0.7 grams. So also not so much hydrochloric acid is given out. Now what really amazes me, the mass of sulfuric acid the mass of hydrochloric acid, but you got 2 moles of hydrochloric acid and 1 mole of sulfuric acid. Just an interesting observation, but it doesn't really. I wonder why that is the case. I know, Wushan, welcome.
Thank you. Hello, Musa.
I think the microphone is
Hi.
me. Oh yeah. All right. So now, before I carry on, I just want to run you through, or maybe let me not say it like that. I just want to recap. So last time when we spoke, I think so far we had done. Let me start from the beginning. So I'll start us there. So we talked a little bit about these phenomena: the number of moles, the mass in grams, the molar mass, the concentrations of substances, the volumes, and then we discussed also the ideal gas equation, which I believe we ought to calculate because, or we ought to know how to calculate because noble gases are discussed as part of physical chemistry in grade 11, but that's also useful for us in grade 12 in some instances. Then we proceeded to continue our discussion from where we left off. When we last saw each other, I believe we talked about finding masses of substances that are products based on the information that's given about the reactants, etc. So the long and short of that discussion is that whenever we have the mass for the reactants and we are asked to find the mass of the products that are formed, then we are, in that case, asked to calculate the theoretical yield. I think we did kind of mention it, Jorge. In some cases, you will have a certain quantity of substance that must react with something. But when you do the calculation, you're obviously basing that on the theory, which will assume 100% of all the material that is in the reaction is going to get used. There won't be residue. There won't be an undesired element featuring and then reacting. But that's not really what really happens. And I'm sure in your experience, you've seen that. Maybe there's some residuals left in the tank. You get some losses on materials that's supposed to be the output, even though it was estimated that so much will be produced. You know those things, most. So then we come up with the concept of theoretical yield. At least that's what chemistry comes up with. And in that concept, we distinguish between the theoretical yield, which is what we calculate on paper, and the actual yield, which is what happens during the reaction. And those two are not necessarily always equal. In fact, it seldom happens anyway, whether it's in a lab or in industry, that 100% of the materials that react are going to give you 100% of the price. Something always stays behind or something else features and disrupts the equation. So now, to make sense of that numerically, there's this calculation called actual yield divided by theoretical yield times 100. So it just shows us by how much the actual yield differs from the theoretical yield that we calculate. And now in this example, we're given sulfuric acid, which reacts with ammonia gas, to produce an ammonium sulfate fertilizer. And then, oh, you know why this is fertilizer? It's fertilizer because fertilizers are typically recommended based on how much nitrogen, potassium, and phosphorus they have. So because this has quite a high number of nitrogen atoms, it's got, or maybe not. Maybe not. I was thinking of the hydrogen because then it would be 8, but it's fine, it's just 2 nitrogens. But the point is, the nitrogen is part of that nutrient complex. Yeah, I'll just leave it at that. So anyway, we balance the equation. So we have our aqueous sulfuric acid, which we add with our gaseous ammonia, and then that gives us an aqueous ammonium sulfate. And we checked the atoms, or rather, the elements, atoms, etc., in each side of the equation to see if they balance, and indeed they balanced. Now, in this particular example, we're told that we must find the number of moles of sulfuric acid. When we proceed to find the number of moles of sulfuric acid, once we're at this stage where we ought to find the mass of sulfuric acid. Oh yeah, we asked to find the theoretical yield. So in finding the theoretical yield, we have to first start with finding the number of moles of sulfuric acid in the reaction. Now, before I carry on with that, since we're still at that stage, it's important to note that we are given the actual mass. So this is the actual yield. It's the actual yield because it's now what's recorded. So from whatever it is that was mixed together, when the result was inspected, the actual yield was 2 kilograms of sulfuric acid was used, and actual yield is not the sulfuric acid. I'm so sorry for misleading you there. The actual yield is this one here, 2.2 kilograms of fertilizer. So this is the actual yield. Let me erase this so it looks like the word yield. Okay. So that 2.2 kilograms is the actual yield because that's what's recorded as having been formed from the reaction. So we just do a quick check to balance quantities. The elements balance out. We've got 8 hydrogens on the left hand side, and on the right hand side 1 sulfur on either side, 4 oxygen on either side, and 2 nitrogens on either side. Then, because we are given the mass of sulfuric acid, then we can work out the number of moles of sulfuric acid. using this formula. And when we calculate it, we first convert the mass of 2 kilograms to grams, because our units in chemistry at this point, they work in grams per mole. So we convert the 2 kilograms to 2000 grams. And after we do that, we take, for each element in the compound H2SO4, we refer to the periodic table to find the molar mass of each element in the in the compound. And then we add them all up and they give us 98.12 grams per mole. And they give us 98.12 grams per mole. Then we divide the 2 kilograms by the 98.12 grams per mole, and we get the number of moles to be just over 20 moles. And it makes sense because the sample of sulfuric acid that was used was like what, 2 kilograms, so it's quite big. Then we look at the molar ratio. Remember, our question wanted us to find the theoretical yield. Okay. So we're still going to get there to find the theoretical yield. But we must note that between the H2SO4 sulfuric acid and the ammonium sulfate, there are only 1 moles in the balanced equation. So there's 1 mole of H2SO4, 1 mole of H2SO4, and 1 mole of ammonium sulfate. Then we can therefore say if the molar ratio is 1 to 1, then the number of moles must be equal. So if 1 mole of sulfuric acid and 1 mole of ammonium sulfate are represented in the chemical equation, then it means the number of moles allocated to each of them as per their circumstance is equal. Now we use that information for the ammonium sulfate. So now that we have the number of moles, and we can read off the molar mass of the periodic table, we then need to find the mass of this ammonium sulfate. And in order for us to find it, we simply manipulate this equation, N equals small m over large M or capital M, and make the small mass the subject of the formula, which when we do and we substitute, then the number of moles becomes 20.383 and the molar mass becomes 114.04. So when we multiply those two, we get 2,324.477 grams, meaning we have to convert this from grams to kilograms. And if it's not shift the comma 3 times, it's divide by 1,000, but you should get 2,324 kilograms. But now this is the theoretical yield because it's calculated. So the theoretical yield is what we calculate using the principles we've been working with so far, we've been using so far. I'm feeling very light. Can I just have some water? Just give me a second. Sorry. So yeah, theoretical yield is calculated yield. But so far, is everything making sense, or you'll wait for recording?
Yeah, I'm following.
You're following. Okay, cool.
Yeah.
I like how you seem very easygoing with science and chemistry, especially the chemistry. Um,
It's much better than maths.
I can understand why. Maths is very abstract. Just to go off topic a bit, I was watching Neil deGrasse Tyson's feedback responding to Terrence Howard, the actor. And indeed, maths is quite abstract. Because Terrence Howard's refutal of maths is that if you have a number and you multiply it with another number, you increase them, right? So like how bacteria multiply. But but that's more of a material understanding of it. When it comes to the abstract nature of doing math, um, any number multiplied by 1 remains itself because you're not increasing it. So therefore therefore 1 multiplied by itself should give you 1. But if we are doing that physically, then the feeling kind of changes. Like it should increase. I mean, if you're going to multiply one human by another human, you get another human, or bacteria multiply, and then you know what? So I'm just thinking about that because we're talking about theoretical, maths being abstract and physics being more practical. So it's a lot like that refutal of Terence Howard's thing where I was listening to it to say maybe he could be onto something but in a different context or for something else, or he's still early stage in whatever he's trying to get at. But it doesn't matter. The scientific community probably would guide him or he would find whatever. But the point is, in maths, things are very abstract. And that's one of the reasons I didn't do very well in math. I got like 69% for high grade. So but I got a distinction for physics. No, wait, was it a distinction? No, it was a very high mark. It was like almost 80%. Yes, almost 80%. So I also understand when you say physics is much better than maths, I totally get it. It's a lot easy to grasp science because you can relate it to so many things that are practical, tangible, that we can relate with. Maar maths, you have to be more imaginative.
Abstract.
It's abstract, yes. So I totally get it. But anyway, back to actual yield and theoretical yield. So the 2,324 is a theoretical or calculated yield. And we have a given yield, which is the actual yield of 2.2 kilograms of ammonium sulfate. Now, this is fertilizer used in agriculture. So, as you can see, there's a difference between the actual yield and the theoretical yield. Maybe it's like 0.124 or 124 grams, roughly 124 grams. So there's a loss there during this reaction. There's about 100 grams that are lost. So now we want to quantify what the percentage yield from that reaction is. And we simply take the actual yield divided by the theoretical yield. So it should give us 0.94 something. And then we multiply that by 100 to get a percentage. And that's the long and short of theoretical versus actual yield. And then the second example that we worked out now, we have to find the masses of reactants and masses of products. So we're just given a reaction, an equation that shows elements reacting and what the products formed are. And we're given that for the first part, which is A, we're given 2 grams of the salt barium chloride or barium chloride. And we must find the mass of sulfuric acid that is needed to react with all of the barium chloride, like all of it, all of it. Now notice it's a very small quantity. 2 grams is like a pinch of that salt, right? If that 2 grams is a pinch of that salt, then we can imagine that it should be a small number of moles, because when we calculate the number of moles of barium chloride based on where barium is on the periodic table, it's a very heavy metal or substance or chemical element. So when we work out its molar mass, we get 208.2 grams per mole. And we divide the mass that's given of 2 grams by that 208.2 grams per mole. And we end up with an answer of 0.0096 moles of barium chloride. And then we compare the number of moles of barium chloride to the number of moles of sulfuric acid. So in other words, when we look at our equation here, the stoichiometry tells us that there's 1 mole of barium chloride and 1 mole of barium chloride and 1 mole of H2SO4. So that means the number of moles must be equal. If that is the case, then we can use the same equation, n equals little m over big M, to find the mass of sulfuric acid that is going to react. And how we work that out? If we substitute here, we put 0.096 for n, and we put 98.12, which of course 98.12 is the molar mass of sulfuric acid as sourced from the periodic table, by summing the molar masses of each of the elements to get the molar mass of the compound. Then we work out or make the mass of sulfuric acid the subject of the formula, and we simply land with 0.94 grams of sulfuric acid are required to react with all 2 grams of barium chloride. It's interesting how just under a gram of that acid is needed to react with that salt, or with 2 grams of that salt. It's just interesting. Then in the second part, the instruction is that we must find the amount of hydrochloric acid produced. In other words, from the reaction, how much HCl is produced, hydrochloric acid. So in order for us to work that out, we must recall that the number of moles of barium chloride is 0.0096. 0.0096, yes. Now if we have the number of moles of barium chloride, then we look back at the equation, we have 1 mole of barium chloride is going to give us 2 moles of hydrochloric acid. We look at that salt because the element that's consistent there is the chlorine element, yes. Then we can say then that the number of moles of hydrochloric acid should be twice the number of moles of barium chloride, and then we get the number of moles of hydrochloric acid is 0.0192 moles. Then we work back to the same formula, n equals small m over big M, and we work out m by making it the subject, small m, by making it the subject of the formula. And when we have made it the subject of the formula, we calculate, then we find that the number of moles of hydrogen chloride or hydrochloric acid, or rather the mass of hydrochloric acid equals 0.7 grams. So this is also weird because 2 moles of hydrochloric acid are produced from 1 mole of barium chloride. But the mass is so much smaller. I would say it's because maybe that element, barium, is quite large and heavy and dense. So that's probably why. But that's just my thinking. Yeah. So that pretty much sums up the quantitative aspects as far as we have to learn them in like an earlier grade, like grade 10. And I think yeah, and then we did some of that those volume calculations. Yes, we did do them. Where we had to find the volume of something based on the stoichiometric coefficients. Do you recall that? Kancane, ne? Kancane. Okay, it's fine. Let's just revisit them. Let's revisit the concept. So we'll start off with, so now this is now our grade 11 work. And we start off with gases and solutions. Guys, I feel a bit lightheaded. I don't know what's up with me today. I think maybe it's because
Have you eaten?
I have actually 3 meals today.
Sugar?
Yeah, but in the morning.
Okay.
But I think it's because
Listen to your body. What do you hear?
it's because I ran yesterday and today, and my body is like, yeah, it's saying. But anyway, let us qhubeka. So for gases and solutions, we recall. So now this is grade 11. Gases and solutions. So we've got standard temperature and pressure, and our standard temperature and pressure stands for, or STP rather, stands for standard temperature and pressure. Standard temp and pressure. That being said, our temperature is measured in Kelvin, named after Lord Kelvin, and pressure is measured in Pascal, named after Blaise Pascal, also a chemist or scientist or something like that. STP refers to 273 Kelvin, and the pressure refers to 101,300 Pascal or 101.3 kilopascal. Again, I'll just make the illustration. So it's assumed that on an area that covers 1 meter by 1 meter, if you project a column of air into the sky, right? A column of air into the sky. Let's just say a person is standing, okay, maybe 1 meter is, okay, if I draw a person, I'll have to draw feet. Maybe it's a rather shortish person. Yeah. So anyway, this space projects all the way up to the universe. All right, or to the sky. To the sky, not to the universe. Now, this 101.3 kPa. It's like saying this space of air here from the ground all the way to the sky exerts 101.3 no 101,300 Newton per square meter, because Pascal is Newton per square meter. But let me just double check. Pascal. Ooh. Yeah, the unit is 1 Newton per square meter. By the way, it's also used for internal pressure inside your tires, maybe stress on materials, like if you pull on a piece of metal or press onto concrete, as well as like Young's modulus, which is, I forgot what, okay, Young's modulus is something else, but yeah, in any case, because I remember we would do these in materials where some materials are elastic, you stretch them well enough and then they get past the point where they can't stretch any longer and they deformed forever and then they stop stretching. And ultimate tensile strength, etc. So the assumption is that that column of air, if you imagine a square meter on the ground, that column of air that projects into the sky, that column of air exerts a force of 101,300 Newton onto that square meter. So if you understand like the weight of that air column, just A and J, on the floor of 1 meter by 1 meter, the gravity is 101,300 Newton on that square meter. That's more or less how you can think about it. So, and then Kelvin, 273 Kelvin is about, let's see, Kelvin, SI unit of temperature. Right, so Lord William Thomson Kelvin was a mathematician and engineer and physicist, mathematical physicist, mathematician. Ooh, there was a lot to this guy. So anyway, 273 Kelvin is the same as 0 degrees Celsius. So 273 Kelvin is the same as 0 degrees Celsius. I think in the previous class I might have not correctly captured it. So that means that means 0 Kelvin equals negative 273 degrees Celsius. So it's winter now and our temperatures are pretty much below 10 degrees Celsius. So that means, negative 273 degrees Celsius is something else. It's something else. So room temperature would be, let me just share this screen, present something else. So I just want you to see this. Can you see that? What's showing on your screen now?
Temperatures.
Temperatures.
Mercury, boils, steam points.
Yes. Okay, cool. Have you ever seen that experiment they like to do at Expo, Excom Expo, where they put a leaf of a living plant inside liquid nitrogen?
And it crumbles.
And then it shatters, yes.
Yeah.
Yeah. So you can see like where they noted where nitrogen boils. Nitrogen boils at 77 Kelvin. So that means it takes quite a very low temperature for nitrogen to be liquid. Do you ladies know what dry ice is? Dry ice.
Liquid nitrogen.
No.
Yeah, we've seen it. That nice one, that smoky.
Yes. There's something else as well called dry ice. Do you know dry ice?
I can't believe you're using Wikipedia, bro.
It's convenient for now. And it has pictures. So dry ice looks something like that, but it's a solid form of carbon dioxide. So if you could freeze carbon dioxide, which I don't know where's its freezing point, but it sublimes at 194.7 Kelvin or negative 78.5 degrees Celsius. So sublimation is to change from one form to the other, I guess. From you, why never but a donation? But does Wikipedia ask you for donations as well, or you don't use it?
I don't use it.
I mean, I could go to like a research article, but that's
Google
so
Scholar.
extra. Google Scholar. That's gonna give
No,
me.
but this is fine. Doesn't dry ice, if you put your hand on it, it freezes.
Yes, something like that. Yes. And it's used to preserve food. And in the deployment of some vaccines, hey, to flash freeze food.
Maybe for transportation, it's like a flash freeze.
Yes. For biological samples from a lab. It's used to make ice cream, to solidify oil spills, and to stop ice sculptures and ice walls from melting. Ooh, interesting. In plumbing, it's used to cut off water flow to pipes to allow repairs without shutting off water mains. Industrial is loose. It loosens asphalt floor tiles. Americans use asphalt different from us in South Africa, so I don't want to use words that have extraterrestrial occurrence. Following the Mars flyby of the Mariner 4 spacecraft in 1966, concluded that the polar caps were entirely made of dry ice. I guess it's pretty cold on Mars. Yeah. Safety. Exposure can cause severe skin damage through frostbite, and the fog may hinder attempts to withdraw from contact in a safe manner. Ooh. Ooh, okay. Let's see. At least one person has been killed by carbon dioxide gas subliming off of dry. Or sublimation is to change, is to skip like a phase of matter. You know how substances go from solid, then liquid, and then gas?
Yeah, this is immediate reaction.
Yes, it goes from solid to gas. Like urinal cakes.
Yeah.
You know what a urinal cake is, right?
A urinal cake.
Cake.
Cake, yeah, that thing to make it smell a
Nice.
certain way.
Yes, to make it smell nice in the toilet, in the public toilet. Yeah, so sublimation is to shift from solid to gas, which is why, yeah, urinal cakes behave the way they do. Yeah. Anyway, So that's the long and short of dry ice and dons. I'll go back to presenting this one. Yes, Jumbo. So that's just to give us an idea of how the Kelvin scale works. I just went off topic there with what's this, dry ice and liquid nitrogen. So anyway, with gases and solutions, starting off with gases, there's this formula called where we use the pressure measured in Pascal, and then we use the number of moles, which is 1 mole, and then there's a gas constant, which is 8.31 joules Kelvin mole, and there's also the temperature, which is 0 degrees Celsius or 273 Kelvin. All right, so this information is what we assume for a volume that occupies the space of 22.4 liters or 22.4 cubic decimeters. And this simply means, and this is when we use the formula P V equals nRT, right? But for a gas that occupies this volume, then the pressure is that much, and it's 1 mole of that gas, with that gas constant being at play. I just want to make sure it shows that it's a -1 there. And the temperature is assumed to be that much, right? So this is 1 mole of gas at STP occupies 22.4 cubic decimeters. And so that's the long and short of it. But what we can deduce from it is that if we had any number of moles of gas, let's say any number of moles, that could be 2 moles, half a mole, 3 moles, 2.5 moles, it doesn't matter. Then that volume becomes the 22.4 dm cubed times those number of moles that we are given. So if we're given 3 moles, we simply multiply the 22.4 by 3 moles. And then that's it. So as an example, we are given 2.3 moles of hydrogen gas at standard temperature and pressure. How do we find the volume? We simply say the volume of that hydrogen gas would be 22.4 times the number of moles of that hydrogen gas. And when we substitute the 2.3 moles there, we get 22.4 multiplied by 2.3, and the answer is 51.52 cubic decimeters. That's the long and short of it. Then sometimes reactions would take place between the gases, and in that case we can work out the volumes of the gases using the fact that the volume is proportional to the number of moles. Okay, so the formula for that in the case where gases react, so we'll have 2 gases, for example, in one system. Let's do this, let's do that. we'll have the volume of the first gas, and it equals the stoichiometric coefficient of the first gas divided by the stoichiometric coefficient of the second gas multiplied by the volume of the second gas itself. So A is stoichiometric coefficient of gas A, whilst B is stoichiometric coefficient of gas B. VA is volume of gas A, whereas VB is volume of gas B. Then, as an example, say we have hydrogen and oxygen. Let me make a new page once. Hydrogen and oxygen react to form water, or rather water vapor. Is this alerting us? Oh, okay, it's fine. By the time we're done at 8, we will not be cut off. Alright, so two hydrogen gas molecules need to react with one oxygen gas molecule to give us two water molecules. So if 3 cubic decimeters of oxygen are used, what is the volume of water produced? Find volume of water. Firstly, we must look at the stoichiometric coefficients. The volume that we want to calculate is V H2O, and it must equal the stoichiometric coefficient of that volume, or rather of that chemical, and it must be divided by the stoichiometric coefficient of the other gas that we already know, and we must multiply this by the volume of that gas that we already know the details of. So since we know the volume of oxygen to be 3 dm cubed, we'll substitute that there. The stoichiometric coefficient of water is 2. So in other words, it's these number of moles here. And the stoichiometric coefficient of oxygen is 1. And that means we simply have 2 times 3. Therefore, the volume of water that is going to be produced would be 6 liters or 6 cubic decimeters. In other words, 2 moles of hydrogen react with 1 mole of oxygen to produce 2 moles of water. And we can also say that 2 volumes of hydrogen react with 1 volume of oxygen to give us 2 volumes of water. So that's pretty much self-explanatory from the equation itself. But we can also make reference to the number of moles or the volumes, so to speak. Kind of like saying, if I'm going to mix Oros to the correct proportion, it's 1 part Oros to 3 parts water to get the original orange squash flavor. And if it's Wild Island, it's 1 to 7. So I'll get 8 parts. If it's Halls, it's 1 to 5. Or is it 1 to 4? 1 to 4, and I'll get 5 parts. Something like that. it's that principle. It's that way of thinking about it. Yeah. Then we can extend this to gas phase calculations. So gas phase calculations. And what does that mean in the context of an example? We are given that 3.3 cubic decimeters of propane are burnt. 3.3 liters of propane are combusted or burnt to give carbon dioxide gas and I guess H2O. So that means if we take C. Oh, by the way, no, I saw this other picture of a clock, right? And instead of numbers, they have these organic molecules. So the first one, so like for 1 o'clock, it'll be C1H4. For 2 o'clock, it's C2H something. You know, like your alkanes.
Ah, I need to Google that. That would be
Yeah.
nice to have in the office.
Yeah.
It would be nice to have in the office.
If I send you the picture on Messenger, will you?
I'll look for it.
Alright, cool. I think I downloaded the picture. Yeah, I think I downloaded the picture. So yeah.
Okay.
So after class, I'll ding you. I'll ding it and then send it to you via Messenger or email. Doesn't matter.
Okay.
Yeah. So we've got propane gas reacting with oxygen. That's the combustion process. Did Musa leave? I think she has gone. Yeah. And then this gives us carbon dioxide, gas, and some water, which is also in gaseous form. So this is 4 water parts, 3 carbon dioxide parts. Yeah. And this balances out because it's 3 on this side and 3 on that side. 8 hydrogens this side and 8 hydrogens that side. 4 times oxygen plus 3 times 2, which is 6. So that's 10 oxygens, and it's 10 oxygens on the left hand side. So everything checks out. Then we must find the question was what volume of oxygen? So find volume of oxygen needed for combustion. Yes, that's what I didn't write down. Then this means if we go to that formula, the volume that we must find is volume of oxygen. So that means this is the stoichiometric coefficient of oxygen, and this is the stoichiometric coefficient of C3H8, and this is the volume of C3H8. All right. Then the next thing that happens, since we don't know the volume of oxygen that's required, but we do have the stoichiometric coefficients of both propane gas and oxygen, as well as the volume of propane, then we can just substitute that information that we have. So we've got the 3.3 for the volume of propane, and we've got the stoichiometric coefficient of oxygen would be 5. whereas the stoichiometric coefficient of propane would be 1, and the answer is 5 times 3.3, and that gives us 16 and a half liters, or dm cubed. And that's more or less how we work them out. So I guess the long and short of it is unknown gas, or rather unknown volume of gas, is VA. Then A is, I guess, coefficient of VA, and B is coefficient of VB, and lastly VB is always given. Yeah, and